As always, just a few important notes before we get started. Some things that are a need to know before you jump into this video, at least to get the most out of it. Basic programming constructs and principles in any language will do. Hexadecimal, decimal, and binary number systems are a must. We'll be talking about those a lot. And even the tiniest bit of reversing debugging and disassembly experience will help you out a lot so you're not totally confused as we go through this video. And if you want to jumpstart on reversing and assembly language in general, I have a what we call colloquially a Master of None course, or basically a long-form tutorial about x86 assembly. Find it on my channel in my Master of None course playlist. And some things that are going to be nice to know, but not necessarily a necessity to know to get the most out of this video. Basic construction of a .NET assembly, and if you are rusty on that, or you want a refresher, or you want a deep dive, the spiritual prequel to this video is our ASyncRAT config parser video that was released a couple years back, and that talks a lot about how these assemblies are constructed and a deep dive into reversing, decompiling, and putting together a different config parser that's going to serve as the foundation for the one we do in this video. Other stuff, regular expressions, malware analysis tools and techniques, cryptography, Python itself, which is what the majority, all of the code is going to be written in this video. All of that's going to help you, but it's not a necessity to understand everything that's going on. And lastly, just as a final note, I'm not an expert in anything, but especially not programming. And sometimes I'll have very experienced programmers come in and be like, do you know this guy who is on this YouTube channel and he claims to be a Python programmer, but he's not even using type hints or anything? And it's like, yes, I know him. He is me. I'm not an expert in that. There's going to be things that people take issue with in my style in this video, I know. With that said, I always appreciate good constructive feedback about things I can improve with my code or styling or bugs or whatever, as long as they're delivered respectfully in the comments. Or you can get a hold of me on Mastodon, InfoSec Exchange, Reddit, and of course the GitHub repo that's linked in the description of this video. That will also be the place where if you have bugs or issues or anything else with the code we discussed today, you can submit issues or PRs or anything else you'd like at GitHub. And finally, please like and subscribe if you enjoy, share it with anyone else you think might benefit from it, and comment what you would like to see in future videos, as well as your feedback, of course, on this current video. Thank you so much for being here for this video, and thanks for watching. Welcome, everybody, and for those of you who have been here before, I know what you're thinking already. A Jeff of all trades video that doesn't have a 3 to 5 minute over-the-top, kitschy, and stock photo full introduction. Has he finally started listening to our feedback and cut those out? No, I haven't, actually. No, I haven't. I didn't do an intro for this video because for those of you who have not been following the channel, it's been a busy time. We just had our third kid. I've been on leave, but it has not felt like leave at all. There's just been so much stuff going on that I'm not going to get into here. But all that in mind, and just the fact that I'm also working on the Master of None course that was requested in the 2024 video we posted earlier, the Malware Sandbox one. Trying to do a bunch of stuff, and this was not intended to be a video, but kind of came together in a way that I thought could benefit a lot of people who watch this channel who are interested in malware analysis and Python as well. So all that stuff came together, all that to say that I didn't do an intro because I'm feeling very lazy after all the work I've already put into all this other stuff going on. And those intros, even though they are silly and they only are a couple minutes of editing with very shoddy editing, they do take more time than I'd like for each video to do. And I'm still going to do them going forward. I just didn't really feel like doing it for this one. There's also not a lot of stuff in this video that lends itself to an intro, even though I've already been talking for a couple minutes. So consider this your intro with all that IRL stuff out of the way, some background about what we're going to be talking about today. 2 years ago, we wrote a configuration parser together for the ASyncRAT malware family. You do remember that, right? Very special night in our lives, right? No? Oh, okay. I thought I must have mistaken you for that other viewer, the more loyal one. No, I'm just kidding. That was a ton of fun. I learned a lot from making that video. I hope you did too, if you did participate. And along with that, some of the feedback I got in the 2024 survey and just in general from comments on Mastodon and YouTube here, a lot of you want to see more malware analysis videos. The only thing you all want more than malware analysis stuff is game modding stuff, more game modding stuff, which is fine. I love that. We'll have more of that soon. Shorter form content, which I'm trying to at least do a little bit more relatively shorter form content. If you look at the ASyncRAT video, you're probably like, oh my gosh, you're going to make something that's shorter than 6 hours. How are you ever going to do that? I know. This is going to be a lot shorter than that. We're not going to go nearly as deep as we did in the ASyncRAT video. It's going to kind of be a high-level overview. I mean, we're going to get deep enough for those of you who are really interested in the mechanics of how the configuration parser works. But we're not going to be building it from scratch. It's already built. We're just going to kind of review it, the code together. And a lot of you, thirdly, I guess, a lot of you are either aspiring or experienced devs or InfoSec people looking at applying coding to InfoSec or looking at upping your dev skills. A lot of feedback has been around that. And I think code reviews like this can really help with that. Again, keeping in mind that I'm not perfect, and you should definitely not copy my code in any scenario and think things will go well for the most part. But I do think it's helpful to talk through and share these things for you as a learner, and also for me. It helps me to get feedback on these tools, especially for those of you who are, actual, SOC analysts or Intel analysts who are using this, who might use it. I would love to hear from you about your feedback. And for you learners, I would love to hear your questions or, anything else that might be on your mind regarding this config parser we're going to go over today. So that's kind of the background that came into this. This wasn't really meant to be a video. This was just a project I was working on based on that ASyncRAT config parser we wrote together. I've been using that not every day, but quite a bit. And it's been working really well. But there were a few things that I'll cover here in a second that were not optimal with that config parser, number one. And number two, there were other malware families. For those who don't know, there's actually quite a few malware families that are, or RAT, Remote Access Trojan families that are based off of ASyncRAT, or that steal or reuse code from ASyncRAT, or that have some kind of derivative. So there's quite a few families that are out there. We'll talk about 4 of them today, including ASyncRAT, that use kind of the same configuration that our parser was set up for. So I really wanted to expand on that parser we built to make it work with a lot more RAT families. In fact, this must have been on some of your minds as well, because one of our viewers, cyMaestro, wrote an awesome Medium write-up on his take on the ASyncRAT parser that he applied to QuasarRAT, which is actually kind of the road I was going on when he posted this. This was an amazing morning when I woke up and I saw this Medium report out, because I was literally in the middle of building out the QuasarRAT portion of the code for my remake of it. And cyMaestro did an awesome job. He basically, I won't go through all of it. I'll link it in the description though. He took our ASyncRAT parser, applied it to QuasarRAT, and got at least the string parts of the configuration out of QuasarRAT, which is awesome. And he goes into detail in his write-up there. Thank you again, cyMaestro, if you catch this video, for that write-up. And for all of you, if you ever do write-ups like that, surrounding or with background to the videos, feel free to tag me. I don't write anything on Medium right now, but it's always cool to see what you all are doing. And I don't always see everything. Most of the time, it's someone contacts me and lets me know that, hey, someone wrote this thing and I found your video that way. So yeah, feel free to tag me there. Anyway, all that aside, so just like cyMaestro, I was working on the QuasarRAT and some other families of rats that share the same kind of configuration, trying to make a configuration parser to rule them all that could handle multiple families. I had made some headway, but I kept running into, reconsiderations of assumptions we made with the ASyncRAT config parser, roadblocks adapting it to new data types. More and more, I kept refactoring, trying to find some kind of least common denominator among all the families that, could be used to parse all of them. And you'll see this project, the Rat King parser, as I'm calling it, is kind of the end result of that. And it's worked so far in testing, knock on wood, fairly well. But I'm definitely looking for more feedback. So again, if you're someone who might use this tool, please let me know if you have other malware families that you'd like to add to it, or if you find anything that's useful or not so useful or buggy about it. So that's kind of the background for this. We're going to be talking about 4 rat families in particular. Like I said, QuasarRAT, ASyncRAT, DcRAT, VenomRAT, ASyncRAT. Obviously, we covered in the last video. DcRAT and VenomRAT are very similar. DcRAT is almost an exact clone as ASyncRAT. VenomRAT is very close to DcRAT. QuasarRAT is probably, this is the one I focus the most time on because it's probably the one that's similar enough to ASyncRAT but has the most changes to the configuration, which we'll see in a second when I pull up the builder here. So that's where I kind of put most of my energy, was in QuasarRAT. And as we walk through these code files, I'll kind of talk you through the journey I had building out this config parser and the lessons learned along the way and why I made certain decisions I made. You'll probably recognize, if you watch the ASyncRAT video, you'll probably recognize a lot of the code that was ripped from there, but it has changed quite a bit. So before we get into, I'm going to pull up my VMs here and pull up an actual QuasarRAT builder. We'll actually build a payload and run it, and I'll show you what that looks like, just like we do with ASyncRAT. I want to talk about a couple of things that were, as I alluded to earlier, shortcomings in the original ASyncRAT config parser. And for clarity, I'm not going to change the parser, at least not in relation to these things, because I think it still stands on its own as a great learning tool. Forgot to close my find window there. But there are things that I wish, going into this config parser, I knew I wanted to make better. The first of those was that I tried not to use any external .NET libraries to interact with the executables. We actually did all of that. You kind of see it alluded to here. We did all the calculations for the metadata in the .NET tables. We did all of the string conversions. We did all that stuff from scratch, which was awesome. That was the intent of that tutorial, and that's why I'm leaving it alone, because I still think it's super valuable to have that experience. The problem with that, and by the way, I think I mentioned it in that ASyncRAT parser video, but the reason I didn't use many external libraries at all is because I wanted to build everything from scratch. But then after filming in post, I realized, or it was even after the video was posted, somebody commented on the GitHub, I realized that the cryptography library is external. And for some reason, I had it in my head that that was a baked-in Python library. Anyway, so the first video ended up not even being pure Python. There was an external library in there as well. Anyway, the problem with not using an external library is that this portion right here, where we calculate the row sizes of all the metadata tables and use that for like translating string addresses to string values, this data doesn't stay the same between samples. Now, when I made the ASyncRAT parser video, I tested this across a few hundred samples of ASyncRAT, but that data was biased in that I was looking at, for the majority part, there were a couple of samples in there that were from different threat actors, but for the majority of the part, I got my data from a few, 2 to 3, I think, threat actors who used ASyncRAT over and over and over again, so they weren't changing their payloads that often. What I later learned is that these row sizes are not guaranteed to be the numbers you see here. They change from payload to payload, dependent on a number of things. So that was the biggest thing that was kind of a drawback when making this new config parser that I knew I wanted to fix, is making sure that we didn't have anything in here that was hard-coded and might change from payload to payload. And that's why it took so long, is because it was difficult to come up with something that was agnostic enough to all these different variations, but still has some kind of least common denominator to work off of. And again, we'll talk what that was in detail in a little bit. But before we hop into the code, I do want to open up a couple of VMs and just set up an environment to, number one, look at QuasarRAT, the builder. We'll have a victim and a server machine, and I'll show you what the actual deployment of the malware looks like, and kind of look at we'll build a configuration ourselves and then parse it with the finalized config parser. So I'll just show you how to set up that environment. If you want to skip this part, that's completely fine. I do recommend, if you're going to use the config parser, to watch at least the second part of that, the part where we are going to set up the parser and download the requirements and install all the different dependencies for it. That part might be helpful, but you can get the same information on GitHub as well. So with that being said, I'm going to pull over what's going to be our server VM here. So let's go ahead. I've got a copy of the Quasar builder here, and you can get this. I don't like to link these in my video descriptions because sometimes YouTube gets a little squirrely over malware or perceived malware repositories getting posted, but you can find it on GitHub, the Quasar source code, as well as the releases right here, and you can download the same builder yourself. So we'll take a copy of that into this VM. These VMs I'm showing, by the way, for those who are interested, these are the same ones we're going to build in the Master of None class that's coming up, but this was kind of an ad hoc, shoddy build of it that I had to do because I was doing some research and needed it quick, so we'll actually be rebuilding this with much better and more updated tools here, but that's neither here nor there for now. So I went into that folder, I just clicked on the quasar.exe, and we'll go ahead and have it create a new certificate, and it might take a while, so I guess we'll wait here for a second. Okay, there we go. Yep, I don't really care because I'm just using this one time. So if you all watched the ASyncRAT video, you see this is very, very similar. If you go to the builder here, we can set up our own config. So we'll just say my client tag. We'll leave the mutex to the that thing. We can check or uncheck this. This is going to translate to a Boolean value. So sorry about that. My recording room is right below my son's room. Same son, actually, who appeared in the thumbnail of the ASyncRAT video. He obviously looks a lot different now, a couple years later. Anyway, he's super clumsy, and he just fell out of bed really hard. He's fine, luckily, but it scared me quite a bit. So I'm back now. We're good. We got the mutex. Like I said, you can check or uncheck that. We'll just leave it unchecked for now. We'll just do a local host. Or actually, I do need to make this. What's my IP on here? I've got these statically IP'd, and I think this is 10.10.10.2. Okay, so we'll set that to 10.10, 10.2, because this is going to be the IP address that our client or our victim is going to connect back to on 4782 as the port. So we'll add that. Let's go ahead and change this to something not default, just so we can see it reflected in the configuration. Let's go ahead and set some of these checkboxes to true, especially this one. Yeah, this will be a good one. We can select which folder we want to install to. We'll go to program files, I guess. That does say it requires admin privileges. That's fine. We'll just keep that the same. We'll call this myrat.exe. I'll leave all those unchecked for now because they don't really matter, as long as we have one kind of as a demo that's checked. We could change this stuff too if we wanted to. This is just the metadata. We could set our own icon. But yeah, this is all the stuff that your attacker, I keep saying those like you can't see me, but it's like I'm saying that with air quotes. It's because I know that some people may actually use this software as, and the authors probably intended it to be used as the other nomenclature for RAT, which is remote administration tool, or a legitimate product. But for the most part these days, it's going to be, not so nice actors who are using this to con victims, basically. So if I use, victim and threat actor, no offense to the authors who may have intended this to be used non-maliciously, that's just what I'm going to be saying. All right, so we could change this. The threat actor could change all this stuff to kind of hide or, stay out of sight or blend in with other programs running, or just throw them off the scent. This is QuasarRAT. You could change the icon. We could enable the keylogger. Let's go ahead and do that. And that should be that. So let's go ahead and build our client. Oops, I didn't include I'm not going to change the assembly information, so let's uncheck that. And we'll just call it something like a threat actor would. We'll call it like a acrobat.exe or something. If I wanted to, I could have put, an Acrobat icon or whatever. So now what I'm going to do is I'm just going to transfer this over to my other machine, my other Windows machine here. I'm going to go ahead and add it to an archive and put a password on it just so I don't accidentally click on it or something. As I transfer it over, we'll use the well-known infected password, put it over in our shared folder. Let me pull up my other VM here running Windows 10, or Windows 7, sorry. I thought this was a Windows 10. And this will be our victim machine. So let's go ahead and pull over our acrobat.zip. And these are all on the same internal network, so they're not internet connected to the actual internet. And we'll go ahead and run that. And let's see what happens over here as our victim over here runs the program and it gets kind of set up. So first of all, let me confirm. I've got my victim pulled up my other screen here. Let me confirm that it's actually connected and it's pulling an IP. And in a minute, if it is, we should be. Oh shoot, that's why I just saw listening false. That would be why. We need to start listening on the port. That's why we should see new connection pop up here in a second when the heartbeat happens on the victim. I'll try to pull these up side by side. Not much going on the victim right now, at least not that's obvious. If you look in Process Hacker, you might see the program running still. And it is, it's right here. Do we see any network activity? There we go. You know what I did wrong is I totally forgot. Remember when we made that option that said you need to run this with administrator privileges? That's what I forgot to do, is run that with admin privileges. So I just did that, and now I see I'm connected. And at this point, the threat actor I'm just going to blow my threat actor window up here. You could do just about anything in this machine you wanted to. We can start the keylogger. Let me hop over to my other machine here and just start typing something random. Why am I having such a problem here with VirtualBox? Well, I think I just answered my own question, because how many times has that phrase been said? Let's see. This is a keylogged statement. Let's see if the keylogger picks that up. Over here, get logs. And yeah, it's actually even, somewhat letter by letter there because of the delay, but you can see that you can do just about anything once you have the actual client running. And you saw on the victim machine, you basically don't have any inkling that anything's going on in the background. I could even, one I always like to show, I think I showed this on ASyncRAT too, is you can get, full remote desktop and see what the person is doing. Obviously, Windows 7 just alerted us to that, but, you could disguise this as, I don't know, some other VNC or other legitimate service, and hide that. And yeah, you get the idea. So I just wanted to demo to everybody what that kind of looks like from a deployment standpoint. I'm going to go ahead and close down my victim machine here. I don't really care about the snapshot because it's wrecked anyway, and I got to rebuild it. The next thing I want to do is show you what that config looks like if we were just to open it up in dnSpy, which is a .NET decompiler. And let's go ahead and close this. I'm going to go ahead and bring back up my assembly acrobat.exe and pull it in here. You're going to see with QuasarRAT something that it does that I think the vanilla baseline version of ASyncRAT did not do, although I've seen samples of ASyncRAT that do it, is they mangle the names of everything. So you see that instead of having nice settings here, I get a bunch of different Unicode strings of characters, which makes it very hard to find the config. So for comparison, let's go ahead and pull in the other samples we'll be looking at today in my little zip here. And I've labeled them all so we can keep track of what's what. So let's take a look at like a blank ASyncRAT, or actually let's take a look at, let's take a look at both. Let's take a look at the blank ASyncRAT config and the encrypted one. And I've said take a look 3 times now. I can't say it. I cannot physically say it again. Let's see what those two configs look like. So in an unobfuscated, unmangled program, you kind of have these nice to look at names for everything, and client.settings is where we're going to find our configuration. This is the encrypted one. So all of these are going to be base64 encoded and also AES encrypted. So we'll need a config parser, or we'll actually need to run the sample to get the actual values for these config settings. The other one called stub here is a blank one that just has placeholder values. So if we go into this one and scroll down, you can see that they just have placeholders here. You can see them in plain text there. So this is what the settings file kind of looks like on the ASyncRAT samples. And you can see the different values they have. So Quasar being obfuscated, what I like to do with these is start by going to the top level client assembly here, and up here at the top, it'll show you the entry point, and usually very close to the entry point. So let's click on that. It'll take us right to main. Somewhere very close to here, one of the first things these rats usually do is read in that config. So if we look at the last thing that's called in main is application.run, and then it has a new object here. Let's take a look at that object. All right, there we go. I just opened up a new tab to compare the ASyncRAT initialize settings function, because you'll see when we go into this, this is the function we loaded into actually, but in the same file, there's an onload function. That is one of the only functions here that's not name mangled, and that's because it needs to be its original name so that the program knows what to do when it loads in. And one of the things it does is call this function here. So let's go down there. That has an if statement at the top that then exits if whatever this does equates to false. And just from experience, I know that within the first few commands, that's going to be when this rat sets up its settings. So let's take a look at what this first command in this function is. And you'll see that it's almost identical to this initialize settings function here. It's just that all these are, again, mangled beyond recognition. So this is our, excuse me, our AES 256 function. You can see compared side by side. Aside from the names, they are almost exactly the same. And the same for all of these. These are all the settings getting initialized. So this section right here, looking at the different, let's go back to the ASyncRAT so I can show you a little bit more clearly. You'll see that when we're running through each of these commands here, we're setting up all the settings or the configuration. We'll use those interchangeably. And it's using that AES 256 object to decrypt all those encrypted settings. So if we go here in dnSpy and click on those settings, or the settings, either the class name or the field name. Well, I guess it'll take us right here because we're in the class already, but let's do the field name. It'll take us down to where those fields are defined. So let's do that in the QuasarRAT. We'll use any one of these. And we see that it looks very similar to the ASyncRAT config with a few key differences. For example, you'll notice that ASyncRAT has mostly string values here. In fact, all of these are string values except for the server certificate right there. While the QuasarRAT one has both strings, or as well as strings, it has also an environment.special folder object, which is program files. That's the folder we set to install to, if you remember. It has an integer here for the reconnect delay. It has some Boolean values here, true and false, for those various checkboxes that we looked at. And what else? What else? I think that's it. And it has some null values here as well. Or I think actually that just counts as an empty string. I'm not sure that equates to a null. Let's take a look actually. Yep, never mind. No nulls in this one, but we will see a null in some other payloads. In fact, now that we've seen the similarities here, let's go ahead and pull in for later. Let's pull in all of the other malware families we'll be looking at today. Let's bring in DcRAT. We'll go ahead and look at this one. These are real malware samples, by the way. I'll give you the wonderful link to, or the link to the wonderful site Malware Bazaar, where you can get free malware samples. Just make sure you download them and extract them into a safe environment before you play around with them. And for example, if I wanted to get a bunch of DcRAT samples, I could do something like that. Bearing in mind that these tags are not always perfect, and they're based on a number of factors. So some things that come up as DcRAT might actually be VenomRAT or some other malware family. So just keep that in mind, double check. This one was confirmed, DcRAT. DcRAT is fun because they usually tell you when you go into the settings, well, when we parse it, you'll see they usually tell you right away that it's a DcRAT. There'll be something in here that says it's DcRAT. There we go. So again, very similar to ASyncRAT, mostly strings. There's one null value here, but even that's just a null string. So DcRAT, very, very similar to ASyncRAT, not too different config-wise. Let's bring in I have two different VenomRAT samples. I think I've got a 32-bit and a 64-bit, so we'll bring those in. Let's take a look at what these look like in their settings. And these are actually also not obfuscated, so you can kind of see the settings right away when you go in here. So VenomRAT has an extra keylog params object as part of the config, as well as server certificate AES 256. Yeah, otherwise this is mostly all strings too. So you can see the pattern here. Like they're very similar outside of, Quasar that has a couple of different settings that involve integers and booleans. So, yep, same thing with this one. Nothing too crazy in there. So after I realized that so many of these different malware families were sharing the same configuration and only slight variations, that's when I really got hyper-focused on building a config parser that could handle all of these variations. Now, again, on the surface, all of these look super, similar enough that writing a config parser shouldn't be that difficult, right, to handle all these very similar payloads. In practice, and we'll talk about it when we do the code review, it was really tricky at times. It was really hard to find something that stuck for each payload that we could work off of to identify this settings or configuration section here. And as we'll see in the code, what I ended up doing, instead of focusing on, like in my older attempts even, you'll see, I'll go ahead and switch over to VS Code here. Actually, real quick, while we have this pulled up, let me take a snapshot in case this image goes down. And while that's running in the background, I'll hop over to VS Code and show you one of my earlier attempts at writing this. And in fact, this is one of the ones I screenshotted and shared to the YouTube channel community. You saw a preview of this, and in fact, these files that I showed in that preview don't exist anymore. Because originally, what I was trying to do is build a base config parser and then have several child classes that extended it. And they would all, kind of have a variation based on different attributes of the RAT payload. What kept happening is that every time I made a new child class, there'd be some other weird thing that was different than the base parser that I had to create a new, attribute or class constant for, and it just wasn't sustainable, extensible. It wasn't good code. It wasn't fun to make. It wasn't the whole data model of having child classes to a base config parser wasn't working out. So, as we'll see in a little bit, I got rid of all of these and just settled on one config parser. And to account for the different variations in these, I had to find something that was constant through all of the different payloads. And that constant thing turns out to be the function that precedes the configuration section. The code for this, you'll see even in the Quasar sample, which I should have kept that class open. Let me go back here for a second. I'm going to have to go back quite a bit. There we go. So even in the really mangled QuasarRAT payload, even though some things are changed here from the config in ASyncRAT, for example, the code for this stays pretty much the same. And you can verify that by going to edit IL instructions to actually see the different intermediate language instructions here, or you can even compare at a deeper level the hex side by side and see that among all these different RAT families, they really don't change that function too much. So that's kind of what I homed in on as my least common denominator, and I'll show you in the code how I use that to my advantage when I wrote the config parser to basically look for this function and then pull the section right below it to pull all the config values without having to rely upon, like we did in the ASyncRAT payload, the regular expressions or a certain pattern or a certain type of config value. I iterated through all of those as I work through here. You'll see in my old parsers that I got here, I have different like flag bytes that would then go into the base config parser, and would then be inserted into different patterns here. And it just was awful to try to come up with different custom patterns to go with everything. Actually, it'd be in this one where I tried to make all these different patterns work across all these different payloads. It just doesn't work. So that was a real quick journey through, number one, seeing all the configurations kind of compared to each other, so you can kind of see that they're pretty similar, but some slight variations, as well as talk to you about some of the challenges of writing a config parser that is workable with all of these. So now that we have defined our problem, I'm going to go ahead and pause this. We'll come back in a little bit. All right, there we go. I'm going to go ahead and pause this Windows VM and pull it aside for now and pull up actually a Remnix VM if you're not familiar. And I'll have a link to this one in the description as well. Remnix is an incredible distribution of Ubuntu that Lenny Zeltser, who is the author, one of the authors for the SANS malware analysis courses, put together. And the site, I think I have the site pulled up in the bookmarks here for the video. Yeah. You can take a look at the site and see all the different tools that are included. We'll talk about this a lot more actually in the Master of None course on building the sandbox, because I always include this as part of my sandboxes, my custom sandboxes. It's a wonderful toolkit built on Linux, and I'll use it here today as kind of our parser testing machine. I'll load the parser code into it, we'll load our payloads into it, and we'll run the parser and get everything set up to run that code so that you can see how the parser works. But just a plug for Remnix in general. If you're a malware analyst, you definitely need to have this in your belt to use. So I've got it pulled up here. Let's go ahead and do the same thing as we did with Windows and pull over those payloads as well as a couple of other things here. So here's my payloads. I'm going to put those. Oh, I had some old stuff on here. Awesome. I'm going to put those right here. And let's go ahead and extract to, let's make a new folder actually called mals and extract them in there. So we separate that from the other stuff we're going to pull out of here. Oh, okay. Yeah. Let me just use 7-zip from the command line here. So mals. There we go. That will extract our payloads. I'll go ahead and get rid of the zip so we don't accidentally run the parser against that. And let's go ahead and pull over a few other things. So first is our code, obviously. Let me just make sure I have the latest and greatest code from VS Code in the background. I'm going to copy that over on the other window or the other monitor here. Excuse me. And then pull that in from here. And when we go, I'll go ahead and demonstrate this. If you look at the YARA on this machine, it's at 402. I was using 4.50 when I made the parser, and so I think what's going to happen, well, a few things are going to go wrong actually when we start to try to use the parser. Let's go ahead and try to run the, oops, I need to get into the download folder. Let's go ahead and try to run the parser right away. And if it's going to complain because I didn't put a 3 on my Python there. There we go. For this distribution, I have to put Python 3 on there. Let's try to run it against something in mals. We'll just run it against DcRAT2.exe. And it's like, hey, you don't have a module named .NET file for Python. Now, if I was internet connected, I could just do python-m pip, or Python 3, excuse me, -m pip install tech-r rat king parser requirements. That's how, most people would install the requirements they needed. Because I'm on a non-internet connection machine, what I'm going to do is actually install them manually. And the way I'm going to do that is just pull in YARA Python, which is the only not the only one. YARA Python and .NET file are the two libraries, external libraries we need to pull over. And like I said in the ASyncRAT parser video, I tried to shy away from external libraries to, write everything from scratch. These two, .NET file specifically, is going to help us out with a lot of the, like I said, we kind of manually made this table in our ASyncRAT config table. This library is going to calculate all this for us because that calculation actually ends up being really complex for .NET assemblies for these row sizes. And it also provides a bunch of other functions that are going to come in handy, as well as some attributes that were really meant to stay internal, but I'll show you that I actually abused those internal attributes to make it easier for us to parse these configs. We'll get to that later. For now, all you need to know is that .NET file is a wonderful library for .NET executables. I'll again include it in the links for the video, but this is by Unit 42, by the way. You can see the code there. So I'll pull that over, and YARA Python is, of course, YARA bindings for Python. So we'll be using that for family detection, and I'll explain that once we get to walking through the actual code. For now, I'm just going to focus on installing these, so I'm going to unzip both of those. All right, there we go. And within each of these folders, there'll be a setup.py script to install these without internet connection. You just have to do a Python 3 setup.py install. Let's see. Oh, I'm sorry. You have to do it, though, from within the directory, or else it's not going to find those things. Oh, and you also have to run it as admin or with root privileges, so with sudo. So you'll see we actually get an error with the YARA Python package, and that's because of a couple of things going on with the mismatch in YARA versions, and also this distribution has a little extra step you have to take here. So let's first of all, let's go ahead and remove the current version of YARA installed by default on Remnix. And that's why I also included a copy of the latest YARA 450 at the time of recording. And we'll go ahead and install that manually as well. So let's go ahead and unzip that. Except I want to do a, there we go. Or not even that. Let's do this. There we go. So let's go ahead and install YARA 450. The way to do that is to go in here. You can find these instructions, by the way, by going to, of course, the documentation for YARA, which tells you exactly what to run to compile and install YARA from source. So we're going to do just that. We're going to go into the directory here and run bootstrap. Also, I realized this whole time I've been mixing my Windows and Linux terminology for stuff like directory and folder, so I apologize for that. It's quite late, and yeah, you know the deal. So after running bootstrap, we will run configure. As long as that all checks out, we should be good to move on and do a make. And finally, a sudo make install. So when we do the sudo make install, we're going to get a message here that the libraries have been installed in user local lib. Take note of that, because what's going to happen, you'll see, let's go back to putting together the YARA Python first, is we're going to probably get an error here because of something that's unique to this distribution. So you may not get this error, you may not have to take this extra step, but if you do, I'll show you what to do here in a second once we run setup again. Oops, and again, you want to run it as sudo. Awesome, so let's go ahead and try to run our parser again. Oops, I forgot to actually go into .NET file and go ahead and set up that one as well. Oh my gosh, every time. You'd think I'd learn by now. Okay, there we go. So everything seems to actually work well with the config parsing, but you'll see we actually got an exception here that says error loading YARA rule, check the rule, or run recompile and retry. And further, we see that this rule, this compiled YARA rule here, which we'll look at in a little bit. If you're not familiar with YARA, we'll talk a little bit about YARA, is incompatible with our version. So when that happens, we can simply run the -r flag here, and that will recompile our YARA rule using the local YARA, what do I want to say, version, I guess. And I'm going to go ahead and feed these results. I'm going to pipe these to Python techm JSON.tool, which is a built-in Python JSON formatter to make these a little nicer to look at. I need to add 3 on here. That's better. So you can see that our parser is working just fine with this one, and it correctly identified with YARA that this was DcRAT. It got the AES key, AES salt, and it decrypted all these values and spit out the config there. Now, what actually didn't happen was that error I was talking about was with YARA is what I was expecting, and it might be because maybe I didn't do the right uninstallation last time. But if you run into an issue where Ubuntu is not finding the YARA libraries, you simply have to do let me clear this up so I can just show you here. And also, I apologize, I just realized that this is probably not a great size to be showing this stuff on. Probably need to zoom in a little bit. So let's do this. So if you do this command, if you just add user local lib to your config here, and then do a sudo, I don't really care that it failed because of permission denied, because I just want to show you these commands. If you run these 2 commands, that will fix any issue you have if your YARA library cannot be found by default on any distribution you may be running on. Just wanted to put that out there because I ran into that issue in the lab, and in case any of you have that issue, that's how you can resolve that. If you have any other issues, of course, please leave me a comment and I can try to help you troubleshoot to an extent. But yeah, I didn't run into that issue, so not an issue for me. Skill issue, it sounds like. No, I'm just kidding. If we go back and we do we don't need to recompile the rule because we already recompiled it once. Once you recompile the rule for your specific environment, it should work from that point forward. Instead of just one payload, let's do every payload in the mals directory, and let's see what we get. And it spits out a couple of seconds later all of the configurations for these different payloads, which is awesome. So this is our ASyncRAT blank. Obviously that configuration is pretty straightforward. There's no AES key. There is an AES salt that's included in the payload, but it's not used for anything because nothing's encrypted here. And our YARA rule successfully identified the malware payload as ASyncRAT. This is the encrypted ASyncRAT. You can see these are actual samples again. So these actually are real C2 servers. Please do not mess with them, navigate to them, do anything with them. These are recent samples too, so just play cautiously. Again, identified correctly as ASyncRAT. This time we pulled an AES key and used that to decrypt these. Same thing with DcRAT, pulled all that stuff. And again, like I said, DcRAT is pretty loud sometimes about telling you it's DcRAT. QuasarRAT, again, we have this weird Unicode sequence because this is a mangled config value name, or config name value, I guess. But we can get a gist of what this is supposed to be by looking at it. This is probably the version. This is probably the C2 server. This is the connection delay. This is the folder it's going to be installed in, etc., etc., etc. And then here's VenomRAT. Same thing. You can see all the decrypted data and the other VenomRAT sample. In fact, the one I don't have in here that we should try it against is, I must have, do I have it in my system still? Hold on, I wanted to get the one we built and pull it over real quick. I do have it here still, so let me quickly move this over. There we go, and we can see all the same stuff I entered in at the beginning of the video for all these different config items. So very cool, it's working. You've now seen the end result of the code we're going to look at. Just to bring it all together, talk about some usage of this thing. If you look at the usage message by typing in tech-h, you can see that we only have a few different optional arguments besides the different files that we're going to parse with this thing. So number one is a debug mode, which is obviously very helpful for if you're trying to debug issues. So let's go ahead and turn that on for this one actually. And instead of piping it to JSON.tool, let's just pipe it to less and take a look at the debug messages. And you can see there's quite a few on there to let you know how everything's progressing with the config parser. Oh, 1 second, sorry. Actually, it might work better outside of less to look at the debug messages here because I didn't redirect the output. So yeah, you can see all the different config parser messages, all the different external library messages coming in here, telling us that everything worked just peachy. And you can even look through here. It's very similar to the ASyncRAT one where it will tell you as it's decrypting and as it's finding all these different values, it'll tell you what the results of all these operations are. So that's the debug mode. Aside from that, other options available are recompile, which you just saw us use. That is using, well, we'll take a look at the script in VS Code where it will look a little prettier, but that's just using a little utility file to recompile that YARA rule with your local YARA version so that you avoid any mismatches in versions. Or if you have, if you make a new rule and you want to recompile it into a compiled version of that rule, you can run that command to do so. Lastly, if you want to use your own YARA rule, like let's say you make your own or you want to test your own YARA rule with these RAT payloads, you can use the tac-y command and point it to, say I had a YARA rule called, let's just do this. Let's make a test rule. Let me put pull it from here. We'll just pull the DcRAT rule only, not any of the other ones, and paste that into our own. Oh no, is my copy and paste broken? If so, I'll cut here and just paste it in a different way. There we go. So there's my raw DcRAT rule over here. No other rule included for ASyncRAT or any other payload family. Let's go ahead and use that utility. Hold on one second. There we go. And this is all in the README. We'll go over this, but this is all in the README, how to use this little file here. We'll compile that to test.yarc. This is basically just compiling our raw rule down into a machine readable, serializable version of the rule. So there we go. I forgot to add my flags there. So let's say we want to use that compiled rule instead of the built-in one with our config parser. We can just do a tac-y yarc, and then we'll run it against Acrobat. There we go, much nicer output. So yeah, you can see there's no match because we only had one YARA rule in there to detect DcRAT payloads, and we didn't have one for QuasarRAT, and so we get no match. All that to show you that if you want to do experiment and use your own YARA rules for new or different, custom YARA rules you made, you can do that with this tool. And if you do that and you want me to add one of your rules to the built-in rule, please, submit an issue or get a hold of me somehow so we can discuss that. All right, so you've now seen the full functionality. We spent enough time, building up to the moment of looking at code. Let's go look at some code. All right, back in VS Code, the way we're going to do this is I'm going to start at our runner program, the RAT King Parser PY that we just ran to, run the parser, obviously. And then we'll dive into these subfolders, which contain a lot of the underpinnings of this parser, the config parser class here, all the utilities that feed into that, the encryption and decryption, all that fun stuff. We'll get to that. And then we'll visit quickly. These will take not long at all to visit the YARA rules. I should have put that in as something that would be nice to know for this video is YARA, but we'll talk about it enough that hopefully you all will have a good understanding of how it's used in malware analysis if you're not familiar with it. And if you are, this should all make very good sense with you very quickly once we get to that portion. But for now, let's focus on the runner program down here at the equivalent of our kind of main function here. If we're running this script, we start obviously by parsing our arguments. And also, let me go ahead and close this. I'm trying to blow this up as much as possible because if any of you are watching this on mobile, I know it's always nice to have this quite large. And for those who are on desktop, hopefully this is also, or if you're watching at a lower resolution, I should say, hopefully this works out well too. So obviously parseArgs does exactly what you think it does. It just is our argument parser class that parses out the arguments like, are we setting the debug flag? Are we recompiling? Are we using a different YARA rule? And you can see here we've set the default. We're using the path class from pathlib here to make sure that no matter where we run the script from, it's going to look in wherever the script's being run and in the YARA rules folder for that path there. This is just a way to guarantee that even if we're running it from if we call that script from a completely different directory, it'll still look for YARA rules, this folder or this directory, wherever ratKingParser.py resides. So with that, I think the parsing of arguments is pretty straightforward if you're familiar at all with how Python handles that with argument parser. That part we can move right past. If the user has passed in that recompile flag or the TAC-R flag, we'll call recompile, which is imported from this file right here. And I guess we'll go ahead and take a detour and just visit the YARA files right here. So recompile.py under here is very simple. It sets up a function that uses YARA Python to compile a raw rule file into a YARC compiled file. That's all this does. And so this function right here is what we imported. By default, it uses these two built-in paths, but you can also, just like we did over in the Remnix VM, you can pass in your own YARA rules to compile using your version of YARA Python and whatever version of YARA you have installed, if you do not import the script, but rather run it on its own. So that's all that this is. The YARA rules themselves, I guess I'll touch on very quickly if you're not familiar with YARA. I'll also include the official YARA site and documentation in the video links, but YARA rules are essentially detection rules that are based on different patterns, and those patterns are classified in YARA using the keyword strings, but they don't just have to be, regular text strings. For example, let's take a look at the ASyncRAT rule. It has some metadata. It's got an author. That's me. Under the strings, we have this one that is a text string, and we have some modifiers like wide, which looks for wide strings or different encoded strings in ASCII, and also no case, which means look for it whether it's capitalized or whether it's lowercase or any variation of these letters, capitalized or lowercase. So that's one form, is as an actual text string. You can have also bytes. So this is saying look for byte in hexadecimal 7E, followed by 3 of any byte, followed by 04, etc., etc. And not listed in any of these rules, but sometimes listed in other rules, is you can actually use direct raw regular expressions as well. I'll also link to the, or I think I already said, I'll link to the YARA documentation and the rule writing page so that you can see how to write good YARA rules. And then every YARA rule has a condition, basically how to evaluate the strings we provided to say whether this is or is not a match for whatever we're writing the rule for. So in this case for ASyncRAT, I'm saying if the payload contains any of these DcRAT telltale strings, do not classify it as ASyncRAT. So that'll basically fail. It'll evaluate to false as ASyncRAT if any of these strings are listed, because DcRAT and ASyncRAT are so common that I had to add in some telltale signs of DcRAT to basically exclude DcRAT payloads from matching the ASyncRAT payload. So if none of those DcRAT strings are present and 6 of the strings in total are present, so any 6 of these are present, and the pattern config string is present in the payload greater than or equal to 10 times, which we'll talk about what these different byte sequences are in a little bit, then this rule will evaluate to true, which means that the rule, or the in our parser, the possible YARA family will be set to ASyncRAT. And you can see that repeated here for DcRAT. I've done the same, very similar thing. I've excluded some VenomRAT strings because these are very similar payloads to DcRAT. Any 5 of the other strings, and then patconfig greater than or equal to 10. Quasar is a little bit different. Any 6 of these strings, which are very unique, at least most of these are unique to QuasarRAT, and patconfig greater than or equal to 10, we'll roll QuasarRAT. And then VenomRAT, 5 of these, and then patconfig greater than or equal to 10 again. So again, just like the payloads, these YARA rules for detecting them are very similar, with very subtle changes to make sure that we don't accidentally misclassify one of the payloads. In fact, let's look at what that looks like if we just go back here and unpause our machine. If I go to my YARA rule, not that one, but the one that's actually included in here. Let's say I take out this condition for DcRAT, not any of the DcRAT ones. And I just say 6 of them, and I take out all these strings. And let's do the same thing for DcRAT. Let's take out the Venom exclusions. And recompile that on, let's do on DcRAT, or actually let's do everything. Let's do everything. That looks good. And let me pass in the R to recompile. So we're going to see some anomalies here. We're no longer getting a match for VenomRAT. Actually, let me make sure. Did I use my correct? I didn't use the right one. That's why we did that. I didn't even notice that I was putting my R flag right up against the Y flag there. There we go. Let's try again. We're still going to get anomalies though, just different anomalies. So for example, VenomRAT is now being detected as DcRAT in both instances. If we scroll up here, there we go. QuasarRAT is fine because it's kind of independent of these other ones. DcRAT still evaluates DcRAT. ASyncRAT still evaluates to ASyncRAT. And yeah, okay, so these worked out actually fine. However, I will say that if the ordering of ASyncRAT and DcRAT were slightly different, you could potentially get a DcRAT reading for ASyncRAT or vice versa. So you can see it mostly in this one. In this case, in the Venom payloads, you can see that they get misclassified if you don't have those exclusions put in there. Just wanted to point that out in case you're wondering why I had to put those in, or if you're not familiar with the YARA and how it works. For those of you who are familiar with the YARA, I'm sure you're wishing you skipped this section now because this is all kind of, cut and dry if you've made any kind of basic YARA rules. Back to the parser. The next thing we do, if whether or not we've recompiled or not, is we start setting up our lists for holding. Number one, our complete list of decrypted configs, which is what's displayed to the user. And there's also a separate list here called results. And the reason I made a separate list here is because we actually have set up this config parser to be compatible with multiprocessing. If you're not familiar with that term, it just means we're going to spread out the work instead of having it run in a kind of a single process that runs on a single CPU. We're going to maximize whatever CPUs we have available to spread out the work. And the way we do that, the way I've chosen to do that at least, is to use the Python concurrent.futures process pool executor object. And how that works is you basically have this with block here. You set up an executor. When we build our executor object and we call the map function, we're going to pass that function another function which we want to run against every object in this iterator. So filePaths is our argument that has all of the different file payloads or the payload files that we've passed in. And so we're going to say, hey, run parse config, this function that's up here, which we'll take a look at in a second, against every file in this iterator right here. Now, because we're using map, we also have, you'll see this function takes in two other parameters here. Debug, which is a Boolean to tell us if we're in debug mode or not, and then the YARA rule path of which rule we're going to use to run against the family detection. Because all of the map expects all of these arguments to be iterators, we have to use a function called repeat, which is imported from itertools right here. All that function does is keep repeating the same whatever you pass to it over and over and over again endlessly, unless you specify an endpoint, over and over and over again. So what's happening is I have to use repeat on these because these are not iterators. File paths is a list of file paths. And so it has, you have multiple files in that list. These are not lists. These are just Boolean values and a string. And so we have to repeat those as an iterator over and over and over again in order to satisfy map. It's basically the equivalent of calling, if I wanted to do it without using multiprocessing, I would say for file path in parsed args.filepaths, parse config file path parsed args.debug parsed args.yara. So it's basically doing that exact same sequence, except we're doing it with the multiprocessing map function in place so that we can take advantage of the power of multiprocessing. And I'll tell you that when I tested this on my machine, it was a stark difference in performance time between not having multiprocessing and having multiprocessing. So bear that in mind. Now, the reason we have a two separate list here is this function map does not block, which means that if we just did like decrypted configs equals that, and then we tried to do some other stuff below that, we may get some unexpected results. And so the way we get around that is we put this within a with block here. When that with block terminates, we will know that all of our sub-processes, our child processes, have all finished and wrapped up, and results should be full of every single result that came from each child process. Then we take results and we put that into decrypted configs and we render that to the user. So this is just a little fail-safe to make sure that we don't access those results before all the child processes we're about to spawn finish, which would not be good. Lastly, after we get the results, we just dump them to the user using the JSON dumps function there, which is just a nice way of formatting JSON. And you see we can pass that to the JSON tool utility to get this nice formatted output here. Additionally, if they're not watching the screen, if you just have this as part of a malware processing pipeline, it's also nice to have it in JSON just so you can read out the keys. It's a very easy to work with format for that kind of information, and something that's already built into most malware analysis pipelines. So with that said, let's go up here to parse config. This is the function that's going to run against every single file path. We are going to set up our logger, and the reason we do this in this function and not somewhere down here is because each child process has to set up its own logging. So we actually run that in the child process. Excuse me. Next, we set up a kind of baseline result dictionary that will populate. If we figure out that this file path we passed in is not a file, after all, that'll raise an exception, and we end up with a very sparse output dictionary there. In fact, let's take a look at what that looks like real quick. If I try to pass in a file that doesn't exist, say acrobat2.exe, it'll get an exception message, and our dictionary will just be full of a config that says exception encountered and describes the exception. And then it will show you the same thing here. So that's all that kind of base what am I trying to say? I almost said boilerplate or baseline dictionary is just a placeholder in case an exception happens. Now, assuming that the file exists, the next thing we're going to do is try to create a custom rat config parser object with that file path and then call its report function. We'll get into this file next because that's their most kind of full file. It's got all the functionality we're going to use to actually parse the config out in that file. And then it has a report function which simply passes back all the details about the config, the AES key, the AES salt, all that good stuff. If we encounter an exception in any part of that process, as you saw, the result dictionary will just get processed or get populated with that exception message, and the user will be notified, hey, something bad happened, here's what we think happened. The next thing that happens, let's assume that everything's worked well up to now. Let's assume that our config parser worked and we have it stored away in our result variable here. The next thing that happens is we try to do the YARA rule matching to see if we can identify the family. And again, we use this YARA rule path that we've passed in. There's a little utility function up here called load YARA that simply uses YARA Python to load that rule and runs an exception if it doesn't work for some reason. And then we try to match it against that YARA rule against that file. And if there is a match, we will display that in the YARA possible family member as you saw. And that's it for our parser. That's the main runner code. Pretty straightforward, I want to say. If you're having a hard time keeping up, you may want to take a pause and go read up on more Python because I know I'm glossing over a lot of the Python syntax and the Python objects. I'm sorry, it's not a Python tutorial. I'd love to do a Python tutorial sometime if you want, even though I'm not a master at it. If that's something you want to see, please let me know in the comments if we want to have more focus on programming language stuff as opposed to this stuff. But for now, I'm going to gloss over that in the interest of keeping this at least somewhat shorter of a video. Now we'll head over to our rat config parser file, which has our rat config parser class. And again, this is going to have all the functionality to actually parse out the config from these payloads. And we may jump around, even as we work through the constructor, we may jump around to these other files in the utils here. You'll see at the top we imported quite a few of the utility files I've included here. What we're going to do is start by looking at this self.dnpp member. So that's .NET PE payload. And this is a custom class I wrote. It's in the utils folder. Let's go ahead and pop that open and take a detour real quick. All right, so .NET PE payload is a custom class, like I said, that's just basically a wrapper around the .NET PE object from the .NET file library we talked about earlier. It does a few additional things as well. So for now, I'm just going to focus on the constructor, and we'll tackle the different utility functions here as we come across them. So it takes in the file path, logs that, it gets the data, the binary data from the file to use for all the different operations we're going to do. It creates a .NET PE object for that file, which is going to allow us to get a lot of metadata from the .NET assembly. And it also calculates the text section relative virtual address and the offset. We're going to use that to do some translations of addresses to strings, not even addresses to strings, addresses to offsets and offsets to addresses later on. We'll get to that in a little bit. But that's all this .NET PE payload is. Just wanted you to see that. We do not set up our AES decryptor yet because we'll do that in this function down here. We have a config dictionary here that we're going to populate as we decrypt the config. And the first thing we do is try to get our encrypted config. And this is kind of where the magic of finding that least common denominator comes into play. So what I've done here is I've set up a pattern, a regular expression here based on the opcodes seen, not in that VM, but in this VM here. Let's go ahead and unpause this guy. And let's look at, let's go ahead and go to one of the more clear payloads to look at it, even though it's going to be roughly the same. If you go here in dnSpy and right click, you can either look at the hex editor directly, or you can go to edit intermediate language or IL instructions and see the opcodes being used here. So basically the opcodes are the next level down from this high level language we see here. And if you wanted to, and I'll include this link as well in the description, there's a Wikipedia article that has all the opcodes and what the instruction they translate to. So you could reverse it by this way by just looking at the instruction name, like LDS loads field, and then looking at what opcode and hex that equates to, which is 0x7e, which you see right here in the regular expression. Or you can just take, let me close this window here. You can highlight this function, right click, show instructions in hex editor, and read it that way. And that's exactly what I did to build this pattern to look for that LDS FLD instruction followed by an address here. So that's why I've wildcarded this. This is going to be 3 bytes here followed by hex 04. And then we're going to see another opcode 6F, which is, if we go back to our reference here, call virtual method, and then followed by another address in 0A. But yeah, you get the idea. We don't need to go through each opcode one by one, but this pattern is basically looking for this function right here, this verify hash function, which turns out to be probably the least common denominator of all of these different payload families. So what we do next is once we find the offset in the data where that function occurs, where am I here? Right here. We then take the start of that offset and use the next method offset from instruction offset function of our .NET PE payload class to convert it to an address where that config starts. What the heck did I just say? Well, let's dive into that a little bit. So back over here in .NET PE payload, this very key but long named function, next method offset from instruction offset, What the heck does that mean? Well, before we go into the code, let's break it down visually in dnSpy over here. So what we've established is that this verify hash function is a pretty good marker for when the config is going to occur. It happens in every single one of these different payload families. That verify hash comes right before the config being constructed right there. So what we can do is make a regular expression, which is what I did back in the config parser class right here. Take the opcodes from that function. They really could be any instruction in this function, but as long as we have some instruction in here, we can get the offset from that in our file data. We can take that offset, convert it to an address, and what we can do is use that address. Let's go ahead and do this visually. If you right-click in dnSpy and go to the metadata row for this method, so again, I'm not going to get too deep into the weeds on this because it's in the ASyncRAT video, but in .NET assemblies, there's tons of different metadata tables. One of those is the method table, which has all the metadata about the methods, including verify hash. So let's say we get the offset to verify hash or an instruction within verify hash as a function. If we translate the offset to a virtual address, we can then look up in this table where that virtual address falls. And as soon as let's say we iterate through all of these, and then all of a sudden we get here, and then our instruction RVA is less than this RVA, meaning our instruction takes place in a function that comes before this function's, or I should say this function, yeah. This, if you're confused by this function name, by the way, this method name, I should say, using the wrong verbiage here. This is a static constructor. And if we go back, we can see that indeed, this is the static constructor. This is the RVA for what's going on right here. So what this function is doing is taking that pattern match we got, getting the offset of where that instruction is in our file data, converting it to a virtual address, and then using that RVA to loop through all these different rows in the method table. And as soon as we come across a function that has a greater virtual address than that instruction virtual address, then we'll return that offset. So I know it's confusing because we're doing a lot of translations from virtual address to offset, offset to virtual address. We have to in order to use the metadata afforded to us by the .NET-PE library, because that works off of not offsets, but virtual addresses. But the data our config parser is using is off of a data offset and a block of data. So we have to do some conversions using this. We take that data, we do some simple subtraction and addition, and then we can convert from offset to RVA, or from RVA, I got it backwards, from RVA to offset, or from offset to RVA with these two functions that are included in the .NET-PE payload. There's some other functions here that I kind of glossed over, but that are important, like bytes to int simply converts the bytes from this structure back to an integer. And by the way, like I said earlier, anytime you see an underscore field in Python, that usually means it's meant to be used internally. And this is meant to be used internally by this metadata table within the .NET-PE object here. I'm actually kind of abusing that to get the value bytes from this object, because basically this is giving us the same data that's available right here in the .NET-PE payload. I'm taking this row here. I am looking at its RVA right here. Well, first I'm going to convert it to an integer. I'm comparing that to my instruction RVA. And then when I get to this guy, when the RVA is greater than my instruction RVA, I'm going to go ahead and return the offset for this function right here. What we're going to do with that offset is we're going to take it right here, work from that offset from the start of the config to a return operation. This, by the way, this constant comes from this utility file, which we can touch on very quickly. It's just a .NET constants file that has a lot of useful opcodes, the virtual addresses of some of the sections, excuse me, and then an enumerable class that simply converts these special folder values to their folder names. What I mean by that is back here, sorry to jump around a little bit, but if we go back to the QuasarRAT sample, which is this guy up here, you'll see that these install folders are encoded as objects. And so if you click on this in dnSpy, each of these common directories has an identifier, and this is basically recreating that in Python over here so that we can translate all the special folder IDs to their names. That's all that .NET constants file is. So going back here, we take the config start we got from the method table. We look for everything that occurs from the start of that function right here, or that method, I should say, the constructor right here, all the way to a return opcode, which takes place down here. If we go to edit IO instructions, you don't see it there, but it is there, right? I'm sorry, you don't see it in the main view right here, but you do see it in the opcodes right here. There's a return statement at the end of that static constructor. So basically we're saying take everything in this block here and consider that our encrypted config. Hopefully you're still following along. If not, it's totally okay to take a pause and refresh, rewind, go back and watch the ASyncRAT video to understand this a little better. All that conversion is done just to get the raw encrypted config. We're back up in the RAT config parser constructor. Next, we have to decrypt and decode that config. Now, because we're working with different types of config items in these different payloads, I actually made another utility class. It's in this config item file right here. We can quickly take a detour to this. So this config item utility in this class are pretty simple to understand if you're familiar with abstract classes or object-oriented programming, but they merit taking some time to understand. We don't have to go through all of these because if you understand one, you understand all of them. But basically, this config item class establishes behavior for different child classes of different config item types like booleans, integers, nulls, special folders, encrypted strings. And what we want to do is basically assign a label telling me what that item is. Is it an encrypted string? Is it a boolean? What is it? And then a regex pattern for how to actually parse that binary data for that config item from our payload. This method will be overridden by the child classes, but this is telling it how to derive from the raw bytes, how to derive the final value for that item. We'll go through an example in a second. And this function is pretty much going to be the same for all of them, but basically just using that pattern and that derive item value function to build a dictionary up that's going to look something like this. Let me put it in a multi-line string here. So you're going to get a dictionary called fields that looks like a bunch of RVAs. Like, so let's say, I feel like I'm missing, is it too many? There we go. No, we'll go with that. Let's say we have, let's take one of the, oh shoot, my VM died. I'll go ahead and boot it back up. 1 second. There we go. Sorry about that. VirtualBox decided to open up a unreachable window for me and prompt me with it, so that was fun. Anyway, back in our QuasarRAT sample, we have, like I said, several different config item types. So we have encrypted strings like this. We have integers like this. We have a special folder value like this. That's kind of a custom or a built-in object here. We have booleans. So we have to figure out ways to parse all of these different values from this block of encrypted data we just parsed out in our last function. To do that, we have to take a look at how each of these is set up at the instruction level. So if we look at, for example, the integer, how is that set up? Well, you have a load integer command right here with a raw value, 42 equates to 1, 2, 3, 4. And then you have a store command here in this field name right here. So if we go back to our code, we basically have implemented that for each item or config item type. So our label is int. Our pattern is looking for the hex 20 and hex 80 commands, which are the, you guessed it, commands for, drumroll, load integer 32 basically, and then 0x80 is store that into the specified field. So that's what the pattern we're using to parse that out of the entire config section is. And you also see we have some wildcards in there accounting for the two addresses that are in between those two instructions. So we make an instance of this. We call its parse from command. We give it some data. And that data is going to be the encrypted config data. So basically this section right here, from here to here. And it's going to look through that data looking for those two commands in that pattern, find all of them, and then parse out both the raw bytes of that object and the RVA for the field name. What do I mean by that? Well, let's keep on using the integer example right here. If you look at the instructions, again, there's a load integer and then a store into a field. However, if we go to the hex instructions, again, hex 20 is our load command. There's the integer. So that's the raw value, is these 2 bytes right here. Actually, I should say these 4 bytes right here, because we're in little endian, we have some trailing zeros. And then the store command, and then the address to the field name where we're going to store it, or the field we're going to store it. What do I mean by that? So basically we're taking let's pull these up side by side. We're taking, in this case, the integer value itself, which is 1, 2, 3, 4. We're mapping it to what we call string RVA. Here is the field name right here, or the RVA to that field name, because that's what's included in the hex data directly. We are later going to convert that into the name, but for now, we're basically storing it like this, where we would just have a dictionary that says, hey, at this RVA, we have the value 1, 2, 3, 4. Later on, we'll convert this to the actual thing that might be, whatever it's called, reconnect delay. But that doesn't happen yet because we're actually going to use those RVAs for different stuff. But I think that example, hopefully that example helps paint the picture. But basically these, helper utility classes, these child classes of config item, are just here so that we can parse out every different type of config item. The special folder config item simply takes the bytes listed. If we go here, go to, where's the program files set up? Right up here. If we look at the hex here, there's a couple commands, and then hex 26, which is, if we go here, the number 38, and we take our custom enum that we defined in that other .NET constants file, we find which one's called 38, and we return program files. It's basically just a simple translation. So again, I don't want to get too deep in the weeds. You can look at the code to kind of take a look at how all these are parsed, but these config item classes are just here so that we can set up a common way to derive different types of config items from the encrypted config data section. So back in decrypt and decode config, now that we understand what those config items are, you'll notice that we're iterating through a list of all the ones we've implemented. So booleans, integers, nulls, special folders, encrypted strings. We're going through each one of those item types and we're parsing them from the encrypted config we got back up here. Now, if that item is an encrypted string config item, we're going to take some extra steps. We're going to translate those string RVAs to their encrypted values. What do I mean by that? Well, when you look at the encrypted string specifically, there we go. Let's take this guy, for example, and we look at the instruction in the hex editor. There's a command for, actually, I should have looked at this first in the IL instruction so I knew which opcodes I'm looking at. There's a load string and then a store in field and then a load string and store in field for each one of these. So if we look at that in the hex editor, load string is 72 followed by an address, which is in the user string table, which is the actual, this guy right here. That hexadecimal that we just read or just saw right here is an address to that string. And then we have a store, which we saw before, which has another address, which is the actual field name. So to get this actual string, we need to take that address we just parsed, that RVA, and convert it right here. So this is another utility function that's in our .NET-PE payload. It simply calls the .NET-PE get user string, takes that RVA, subtracts the base, which is this guy right here, and we get the string value back, basically. Basically, all you need to know about this is we end up with, again, an RVA like this, and then the string value, which is that huge base64 encoded string of blah, 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 blah. That's what we're getting back for each one of those encrypted strings. Next, we're going to actually decrypt each of the encrypted strings using another class that's included in the utils called config AES decryptor, and this is almost an exact lift from the ASyncRAT config decryptor, so I'm not going to spend too much time on it. Basically, if you didn't watch the ASyncRAT video, all you need to know is this looks through all of the AES key setup that happens back. Let's go over to a different payload. Let's go to this guy here so we can see it in a little bit clearer way. If we go back up here, basically reads in all the AES data here, block size, the mode, the padding, the salt being used, and uses that to create a cipher that it used to decrypt the encrypted contents. The only kind of wrinkle that I'll point out for the people who did watch the ASyncRAT payload video is that instead of a single key we're deriving here, sometimes what happens, and in fact, I think this is the case with, is it this guy right here? No, this is the blank one. Where's this guy, WinRAR? Sometimes your AES key will be a base64 value. Sometimes it'll be the base64 decoded, whatever value is decoded from this base64. And sometimes it'll be a base64 decodable value, but instead they'll just use that base64. I know that sounds confusing, but let me try to break it down. When we go to derive the AES passphrase, which is needed to create the cipher, again, I'm not going to get too much into the cryptography stuff because it's all explained in the ASyncRAT video, and I don't want to spend another hour on it here, but when you create that cipher, you need a passphrase, and that's what that key value is here. So let's take this one, for example. It could, depending on the payload, it could be this base64 decoded, which is, I've got it working on my other screen here. I'll pull it over in good old CyberChef from base64 is this value. So that could be our AES passphrase. However, for silly reasons unknown to me, sometimes you'll also get payloads that will use this raw base64 as their key passphrase. So I tried to account for both of those scenarios by basically doing a quick check to see if that value is able to be base64 decoded. If it is, go ahead and add that to a list of candidates and also take the raw value itself, the base64, or the base64 decoded value as well as the raw base64, and try both of those as a passphrase candidate and see which one works with the cipher later on. You'll see that come up. Let's see, where is it? If I go down here and look for where those show up. Yeah, when we're doing the actual decryption, we try each key candidate, and then the final key is set based on whichever key candidate actually decrypts the content successfully. So again, I apologize if that's confusing. If you didn't watch the cryptography section of the ASyncRAT video, I would at least go back and watch that chapter so you can tell exactly what we're doing here. But the decryption is basically just parsing out all the data that goes into the cipher, recreating it in or actually let me show that part at least, recreating that in Python right here with a cipher, AES cipher right here, and then using that to decrypt all of the encrypted strings one by one here. So This is, again, only if they are encrypted strings, because otherwise we're just going to get raw values back. For Boolean values, we're just going to get a true or false. For integer values, we're just going to get an integer. For special folders, we're going to get a folder name. So only for the encrypted strings do we have to go through that process of creating a decryptor and then decrypting each of them. So after we've gone through all the config items and we're sure that we've parsed out all the ones that we have implemented a pattern for, and we put them into our config dictionary, the next thing to do is, again, remember, right now they're all kind of sitting there with the keys being in RVA like this. I'm just gonna make it short like that. And then, decrypted string. At this point, we've decrypted all the strings, but the next thing we have to do is translate this address from a virtual address to an actual value. Now, in some cases, where the payloads have plain text values like install folder and install, that will be fine to read out in that JSON output. But as we saw earlier, if you have like the QuasarRAT scenario where all the names are mangled, you end up getting a bunch of Unicode gibberish back in your config, which is fine. The reason I left it like that and I didn't try to do any kind of conversion from mangled name to something logical is because different payloads, even within the same malware family, can sometimes have different fields that aren't present in other payloads. So I figured it was easier to just have the user kind of based on intuition derive what these values are meant to be, rather than try to translate them, as many other config parsers do, for these payloads into their actual values, because it gets difficult when you have payloads that differ in what they the different config items they have, I guess they'll say. So pretty much if you're looking at this, even though the name is mangled, you can still tell this is probably a version number, this is probably the C2, this is probably my delay connect thing. On and on and on and on. So that translation is done here. And again, we're just using a utility function from .NET PE payload that simply converts that RVA to an integer and then looks it up using the .NET PE library and those metadata tables again. So basically it's taking that field. If we go visualize it in dnSpy, it's taking the RVA for the ports field, for example, and then just backtracking, reversing that to find it in this table and grabbing the name ports from that to put that into the dictionary. Just translating an address to an actual name. And then the only other thing to really discuss in the config parser is the report function, which simply returns that JSON dictionary of the file path, the AES key, the AES salt, and the final decrypted config, which then, if you remember, gets bubbled up here. We add the YARA possible family and we return it to the user. So with that said, I think we've covered just about everything. There's a couple of small files here, like the config parser exception, which is just a custom exception class to use so that we can have we can raise a custom exception so that the user knows that our config parser is throwing the exception. Besides that, I think we covered just about everything. There's a couple of utility functions that I'll let you look at, but these just, do simple conversions from bytes to integer, decode bytes. These are also the ones that came from ASyncRAT, so pretty familiar if you watched that series as well. One thing I didn't mention is that I did include a little shortcut import here in my init file. So if you're not familiar, these init files they basically denote that this config parser directory can be imported or has things to be imported. And when you add a line like this, you basically make it easier. So like what that line does is back in my runner program here, actually, instead of typing out from config parser dot rat config parser import rat config parser, which is a very long thing to type out, I can just type out this from config parser import rat config parser. That's all that little line does there. Now that I've covered those few little things, I think we've covered just about everything in this parser. So again, the purpose of this video was not to, overwhelm you with the details, every little detail of the code, but basically to walk you through the challenge I had in trying to create this project that encompassed not only QuasarRAT and ASyncRAT, but multiple other RAT families, trying to find that least common denominator of identifying what can I use to mark the configuration section for each of these payloads, which ended up being this guy right here. Okay, after we did that, how do I come up with a reproducible method to get from identifying this function to finding the config? We did that by using those .NET PE payload functions like this guy to reverse any instruction from this section, get its RVA from the metadata tables, get the next function after it in those same tables, and then identify our config section. And the end result is that instead of having, like I did in my old version, several child classes with a different config parser for each family of RAT, we now have one config parser that has the ability to parse out any payload or any RAT family that follows that same kind of settings module that's imported into all of these, while also providing the flexibility to do some YARA detection and provide the user some input, at least some possible options for what family of RATs comes from. The most important thing I found, and I think I mentioned it earlier when making these config parsers, is for the most part, people are looking for data that's going to help them detect these, and that's going to help them track down other indicators of compromise to help in their investigation if someone gets infected. What that means, what that translates to, is that for the most part, people are not so interested in these little different, settings that are used. They're more interested in stuff like, hey, where would it be installed? Okay, application data directory. Hey, what's the C2 port and IP or domain? Awesome. Hey, what's the delay on how often it tries to reconnect, so I can look for that in my network traffic? Okay, cool. Where are the logs stored? What kind of folder names should I be looking for? What kind of mutexes should I be looking for? What kind of file names should I be looking for? That's the key to these config parsers. And that's why I love building them. It makes my job a whole heck of a lot easier later on, because now instead of manually going through and running a sandbox against QuasarRAT, every QuasarRAT sample I get, and trying to get the sandbox to spit out the C2, I can just parse it without even running the file using these config parsers. I don't need to worry about the family of RAT. As long as it's implemented in the parser, I can integrate this programmatically because it's written in JSON. I can put this into a malware analysis pipeline where I could submit a malware payload to a sandbox, but before it goes through the sandbox, it runs the config parser and spits that out. The options are endless, and I get really excited, as I'm sure you can tell by my breathlessness of talking so much. I get so excited at when these things are successful, and that's why I really wanted to share this with you all as a learning experience, as a kind of hurrah at seeing this all come together. And again, my final ask is that if this is helpful to you, please let me know. If you have issues with it, also let me know. If you have things you want to see added to it, I want to hear those. Especially from the more experienced viewers out there who are SOC analysts, Intel analysts, developers. This is just a beginning of sorts. I'm sure there's more payloads out there that this could apply to. I'm sure there's things that could be cleaned up. If you liked this or disliked this format of video, let me know. Again, this was kind of a whim. I thought it might be helpful, but maybe it was a lot of information at once. Maybe it was overload. Maybe it wasn't as pertinent in video form. I don't know. You can tell me. But I'm putting it out there just in case it's helpful to anyone else who's interested in building out this kind of tooling in your malware analysis pipelines. With that, I've talked with you enough. I'm looking forward to reading your feedback in the comments, in GitHub, on Mastodon. Thank you so much for joining me, and I'll see you in the Master of None class coming up.